Welcome to yet another exciting episode of Machine Design! So, on today's action-packed episode, we will be discussing fatigue. Again. Because we're trying to exhaust the topic. So, with fatigue, on the last episode of Machine Design, what we learned was that in order to calculate fatigue, what you have to figure out ultimately is you have to determine what what's called the endurance limit is. And the endurance limit is a factor that ultimately defines how much a material can handle stresses. You can look it up on a table. Sometimes if you're using a certain kind of material, you can look it up on an SN table, and this is the SN, this is the SE value. If you have 1,000 cycles, your SE value is whatever that is. You can look that up on a table. Doesn't always tend to be reliable, but it happens. So, find SE. You always have to do this for every fatigue problem. You will have to, no matter what, we're going to talk about it today, you always have to find what the endurance limit is. So, find the endurance limit. You can use a table, such as one that's already existing. Do note that the table usually has to be for the right geometry and the right material that you're dealing with. So, yeah. You can use equations. I gave you the equations last time for I gave you the equations last time for ooh, hold on. Interesting. My computer decided to freak out. So I said, oh heck no. Okay. My apologies there. So you can find it from tables, if tables are available. You can find it from the equations, like the equation that I gave you last time, which particularly was only applicable for steel, so etc., etc. There are tables in the back of the book that do talk about endurance limits at certain loading values. There are ways of modifying those values because, you know, we always adjust things. Those equations are given in your book. We're not going to be talking about them because, quite frankly, this is already my third lecture on fatigue, and I'm getting fatigued of it. Okay, so with fatigue, you always have to find SE somehow. Could be an SN diagram, could be a table, could be calculations. Whatever the case. Then, what we're going to be talking about today is effective stresses. Okay? As we mentioned last time, all of the discussion, the failure or criterion that I gave you so far has been for fully reversed loading. We're going to talk about that a little bit more and about what that actually means. And this is one of the reasons why I'm giving you so many lectures this week, is because we just didn't get to all that content. There's a lot to talk about when it comes to fatigue. I wouldn't say it's a particularly horrible concept to understand, but it's definitely something that warrants a lot of conversation because it's a novel concept that you haven't dealt with before this class. This is brand new content. So, when we're talking about effective stresses, if you have, say, beam, and you pull out a member like this, and you know you got your normal stresses, and you got your tensile stresses, and you got your shear stresses. You know, you've got all this stress conditions going on one little piece. It turns out that if this beam were to suddenly jump out like this, that the effective stress at this location does not look like that anymore. It's not even less than that. It's actually greater than, because it's a transition period between over here where you have some amount of stress and right here where you have almost no stress, because that stress is being channeled like this. All that force, all that load is being carried across the notch. Anytime you have a change in geometry, you are going to experience a change in stress values. Now, it would be easier to calculate this using SolidWorks, but we do have, in this book, we do have some assistance in trying to find those values. So it's coming to notch sensitivity, which is section 610. Notches, you look up section 610. The equation that is given is that your sigma max value is equal to your Kf times sigma naught. So if you calculate what your stress value is, your maximum stress value, you have to multiply it by some stress factor based on the geometry, and that's how you find your maximum stress. So this is section 610, walks through a little bit of the calculations. I'm not going to go too far into this, but what you'll end up having is you have these diagrams that are located at the back of the book. There's one located in section 610. Basically what it shows is it's something that looks like this. It's got all these lines, and it's got a diagram of, okay, this is, it's got radius r. And then this line will represent r equals, d over d or something. And r equals 2d over d, and it continues going upward. I'm looking at the wrong figure. My apologies. And on the bottom here, this is then, that's wrong. The one that's given in your book is SUT values equals some number. So this is an SUT value, this is another one, another one. And as the notch radius grows, you see that the value slowly increases to some certain nominal value. This is the, on this side is the sensitivity value Q, which is just, basically it's how much it's increasing by. Okay, so with larger radii, you're going to have much less sensitive, well, you're going to have a factor that's closer to what your nominal stress is. I am not just doing this graph justice. I should have looked it up in the back of the book instead of in the section. So the back of the book is the one that I'm mostly referring to. Let me redraw this real quick. Ignore what I just told you. There we are. So, it's table A15. Here, what it shows you is, let's say you've got a round shaft with two different diameters, and it has some hip with radius r. The ratio of bigger diameter to little diameter, as that changes based on the radius of the curve to the little diameter, is given based on that KT value, which is ultimately used right here. Okay. That table does not look like this, which is why this was so confusing to me. I was describing something else and I used the wrong table. Again, my apologies. The table looks like this. Okay, where these are different d over d values, so maybe this is d over d equals 1.5, this is 1.2, this is 1.05, something like that. And your Kf value on this side, and then your r over little d value over here. So as it changes, as this changes, the geometric changes can give you some very similar KF properties. And if you just go up and look on this and say, ah, well, it looks about 1.4, that's about good enough for us. I hate to say it, but we don't have to be super approximate here. But just looking on the table helps. You'll notice that as R over D becomes greater, meaning you have a larger radius, this really approaches 1. Which means that the sigma max is equal to whatever your sigma max value is that you calculated before taking into account your notch. Okay, so having stress concentrators is important, and you do need to understand that geometric changes do cause stress changes. That is also very true for fatigue. So this is a modification of what the stress is. But we may have a different situation entirely. So far we've only been talking about fully reversed stresses. What that means is that if I plot sigma versus time, the value here goes like this, where the amplitude is this value, and the medium value, if we average this and this, ends up being 0. Okay? So what I'm going to now change this. Instead of saying, well, this is just, you know, an oscillating sigma sine omega t, instead of just calling it this function where, oh yeah, you know, it reaches a maximum stress of sigma, I'm not going to change the terms. We're going to go ahead and define this value right here as sigma A. Okay, and what that stands for is sigma amplitude. Okay, and then the median value is going to be the value that is directly halfway between these, which happens to fall on 0 for this, which we're going to call sigma M, which stands for sigma median. Okay, sigma A equals amplitude, and sigma M equals median. Median stress and your amplitude stress. Your amplitude stress is half the distance between the two. Your median stress is the middle point between the two. Okay, so your median stress plus your amplitude stress is going to equal your maximum stress, and your median stress minus your amplitude stress is going to equal your minimum stress. Okay, so this value right here is equal to sigma M minus sigma A, and this value right here is equal to sigma M plus sigma A. And this value right here is sigma M. Now what this allows us to do is we can now use these definitions to shift where 0 is. It no longer has to fall on 0. We no longer have to have what's called fully reversed loading, because in fully reversed loading, sigma M equals 0. In non-fully reversed loading, sigma M no longer equals 0, and now we have a loading condition that looks like this. This is not as severe as it would be if we were to take this maximum value and fully reverse it every time. So we are going to get a different set of failure conditions. And this set of failure conditions is actually very close to what we're really looking at for the total failure conditions for fatigue. And I need to adjust your reading assignment for this week. For those of you who may have already handed it in, I'm going to be adjusting this, and because I forgot to include this section on the reading assignment, and I should have. There's only a few questions. I think I might have. I don't know. I'll have to look, but I need to make sure that your reading assignment covers this. So if you've already done it, you've already handed it in, awesome. Otherwise, I'm going to be adjusting it right after this video. That's awesome. Okay, so just make sure to do your reading assignment, check your reading assignment, and it is going to be updated within the next 15 minutes. So when it comes to effective stresses now, we need to understand that not only does your geometric changes affect what your actual stress is, which this KF value would be multiplied by sigma M and sigma A to get different effective stresses, but you also have to take into account median and amplitude stresses. Okay, so all the work we needed to find SE remains the same. And in fact, the process here remains the same for finding all of this, but now we have to take into account the fact that we have median and amplitude stresses. And this is only one little element that makes it slightly more complicated. The calculations that you need to do to calculate fatigue failure, they very clearly state where sigma A and sigma M is. And just a matter of finding those stresses, those should be given to you. You know, it should be given to you somehow that this is a maximum, this is a minimum. To find sigma M is going to be equal to sigma max plus sigma min divided by 2. Sigma A is equal to sigma max minus sigma min divided by 2. So sigma max with time versus sigma min with time divided by 2. You go find where its maximum is and where its minimum is. You will have to calculate stress at that location at 2 different times. Okay, that's what's needed. So if you have a cyclical loading where, I'll say that this is a shaft that undergoes this shear loading, but it's also under tension, okay, which means that your sigma M value, your sigma X value in this direction, it already has some pretension because of this, but then it changes between in bending stress. You would end up with a cycle that looks like that, where it's offset. Sigma M actually ends up being whatever your tensile stress is based on the pole. Anyways, with having this value, you would get a graph that looks like this, and your sigma amplitude would end up being your bending stresses, and your sigma M would end up being your tensile stresses. But you would have to calculate what the x directional stress is, or more so what the principal stress is at the maximum loading position, where it's at its maximum, and then where it's at its minimum. So here, when it's rotating in this direction, and here this is in tension, you rotate it around, and then it's in compression. When it's in compression, then you're at a minimum. When it's in tension, then you're at a maximum. Okay, so knowing these two values with time for a single stress element, when it reaches its maximum and when it reaches its minimum, gives you the median and amplitude stresses. And these are necessary for figuring out what the failure criteria is. So let me show you the process. Last time I showed you the process for stress with a fully reversed loading situation. Now we're gonna add one little simple step that's gonna help us understand what stress is, what the stress conditions are with a non-fully reversed loading cycle. Okay, so first you start out with your geometry, just like last time. You figure out your loading. Okay, from your loading, this is where you come up with your normal forces, your axial forces, your shear forces, your bending moments, and your torsional moments. From that, all of those loading conditions go into determining stresses. Your normal stresses, your shear stresses, your bending stresses, and your torsional stresses. Okay, where your shear and torsional stresses are shear stresses, and your bending and normal stresses are normal stresses. Okay, once you understand those, then you add them together, figure out their dimensions, figure out their directions, and you come up with your 6-axis stress conditions. Okay, that's where you have a sigma x, sigma y, sigma z, tau xy, tau yz, tau xc. Okay, once you have your 6-axis stress conditions, you then come over here and you figure out your principal stresses. Okay, just like last time, you arrange these principal stresses so that it's sigma 1, sigma 2, sigma 3. Okay, awesome. Now you have sigma 1, sigma 2, sigma 3, and you have it for one time t. So you have sigma 1, t1, sigma 2, t1, sigma 3, t1. Where t1 is maybe a maximum. Okay, then you go back and you have to do this again with loading that is now reversed direction to find your minimum. Your minimum loading conditions at this point are going to be your minimum stress conditions. Okay, so you go back to this point, look at loading when the loading is a minimum. You calculate the stresses, you calculate the 6-axis stress conditions, you calculate the principal stresses from that. From that, now you have sigma 1 T2, sigma 2 T2, and sigma 3 T2, where this is max loading and this is min loading. Okay, from these you can now figure out what your amplitude stresses are. If we're just looking at sigma 1, which is your maximum principal stress here, just looking at sigma 1, you find then your sigma A and your sigma M values by using those two formulas. These two added together divided by 2 is equal to sigma M. These two subtracted from each other divided by 2 is equal to your amplitude. Okay? Once you know these, then you plug it into your fatigue failure theory. Okay, which I'm going to give you a few examples real quick because quite frankly the book just kind of word vomits at you. It just doesn't even explain them, just starts throwing them at you like fun times. I can show you, it's on page 314. It's a solid page of failure criteria for fatigue. It's fantastic. You really want some fun times, go through and try to figure out what the difference is between them. But then you can use this to calculate your safety factor. Okay? And this right here is the most complex we're going to get in this class. This is it. It does not get harder than this. Because this is a lot of work. You have to go through this system twice in the same location based on two different loading conditions at that same place in order to find these two values in order to figure out whether or not it's going to fail. Okay? So it's a lot of busy work. It's pretty straightforward. You follow this process. We've added a few steps from static theory, but really the static theory, the only thing we've added is we changed this from static theory, which means we do have to find what the endurance limit is still. By the way, endurance limit. That's a step we had to add for fatigue. We now had to add this step also for fatigue, and you'll notice that sigma M, sigma A, again for fully reverse loading, sigma M is equal to 0 and sigma A is equal to the amplitude of the stress. So it actually makes all of the fatigue failure theories end up just being sigma max divided by N is equal to SE over sigma max, or sigma 1. You come up with that, and then that's your safety factor. Now, most of the other failure criteria for fatigue end up boiling down to that. So let me give you those equations real quick. I'll leave this up here to look at. I should have eaten lunch before giving this video because I'm pretty sure you can hear my stomach rumbling again. I have some powerful hunger. Okay, so in bold, the Soderberg method is sigma A over SE plus sigma M over SY equals 1 over N. Easy to find the safety factor. That's it. With sigma M being 0, this boils down to the equation I gave you before for fully reversed loading, as I said. Okay, then you got the modified Goodman, which is sigma A over sigma E plus sigma M over SUT equals 1 over N. Notice this is for brittle failure. Awesome. Okay, this is for ductile, this is for brittle. Then you got the Gerber method. Gerber, it does explain this a little bit better in the text. I think Gerber's just fun to say. Whatever. which is your safety factor times sigma A over SE plus your safety factor of sigma M over SUT squared is equal to 1. It does give you a little bit of a different failure criteria. It kind of shows you, I believe, it shows you what the differences are on this table here. Oop, this graph right here explains that here you have the modified Goodman line. Modified Goodman line expects it to fail anywhere here in this range that's that's on that line. But realistically, modified Goodman isn't always perfect. The Gerber line is a little bit less conservative. Modified Goodman line is fairly conservative. Soderbergh line is very conservative. So, yeah, just lots of different failure theories, and which one is right? Well, you gotta kind of test to figure out. But at the end of the day, I would just be happy if you used one of them correctly. I like Soderbergh. Soderbergh is conservative and gives you a good estimate, which I like. So this is probably the one that we're going to be using. I don't know if I'm ever going to give you any homework problems that are using the other ones. I might, just to throw things up, but when you do your analysis at the end of the semester, I am going to expect you to understand and use Soderbergh. Okay. I do have one more lecture I want to give this week. It's going to be an example on static failure problems pertaining to last week. If you have any questions on the homework, hopefully that lecture is going to address them. Otherwise, this is the entirety of the discussion that I have for fatigue, and you will have homework over this next week. We will be doing in class this week an example using fatigue where we're actually doing a variable loading, non-fully reversed loading cycle, something or other. And that's what I'm going to stream on Friday. So, okay, ready break.